Thank you, Lucas. Hello, everyone. My name is Suman, and I'm presenting my PhD. So my PhD is about modeling and diagnosis of soil constraints using readily available data sets. And my supervisors are Keith Pemberton, Chloe Lai, and Craig Lovesey. So in Australia, we have 77% of soils that have single or multiple soil constraints, and it is also stressed by the farming group. They have subsoil acidity. And the problem is the extent and impact of these soil constraints is largely based on soil surveys and expert opinions, which may not be accurate to make informed farm management decisions. And the solution is the laboratory method, which is very expensive and laborious and time consuming. So we need something that we can do it cheaply, and that's modeling. So my whole PhD is about how a modeling approach can be fit into existing data sets so that we can get some insightful information from it, and then we can predict soil properties and soil constraints. So this is my first work, which has been already presented in a couple of soil CRC conferences, but I will just briefly talk about it. So the first work was to build a framework that can diagnose soil bucket size. And in that case, I gathered some easily available data sets like the farm management data, soil properties data, and crop yield, which I fed into AppSim, and then I forced AppSim in the inverse direction to predict soil hydraulic properties like crop lower limit and upper limit, so that I can predict PAWC. And the result is just here. It shows that it has a good accuracy to predict the bucket size. And the implication of this is it helps us to identify different types of soil water-related constraints, and it also helps us to make agronomic decisions like the irrigation and sowing time. And the second work is I moved on to the machine learning, where I bought the easily available observed data sets across the national database, and then I applied the machine learning algorithm to build a model of 5 different soil properties, which is shown in the table. And those are pH, electrical conductivity, sodicity, chloride, and effective cation exchange capacity. But out of these 5 soil properties, the result shows that the model can predict pH, EC, and cation exchange capacity with accuracy, but it has slightly low prediction accuracy with the sodicity and the chloride. And we believe that the ESP and chloride cannot be easily predicted by only the observed data. And in my third work, what I did was, so it looks pretty big figure, but it is like in this figure, I tried to predict 4 different soil chemical properties, that is aluminum, boron, ESP, and chloride. But in this case, I gathered around 40 environmental covariates and observed data, which are easily available across our national database. And then I applied 5 different machine learning algorithms so that I can compare the result of those 5 models. And this is the result of the third work. So in this, you can just focus on the one with the black box. So that one is the random forest really perform well for all the soil properties for aluminum, boron. And so in this case, when we use observed data and the environmental covariates, we can predict soil properties. And the implication of this, and the implication of my PhD is that we can predict soil properties if only with using easily available data sets. So we have a lot of data sets that is available across national database like Silo, like ton data sets, and we can download them, and then we can build a model, and then we can predict soil properties. And I also found one important thing is that when we have observed data available, that we should use in the model, because observed data were found to have important contribution in the model. So the PhD and this whole project helped us to understand the different soil dynamics, and acknowledgement to all these organizations. And at last, before I go, thank you so all CRC for this having me as a PhD student. Thank you, Lucas. Thank you.